In this unit, we are going to learn how to perform auto-calibration in HEC-HMS. So to do that, you need an existing HEC-HMS model that has observed data and a simulation that already been run. And what we have here is Cedar Creek model that was created in module 7. So I just copied that into a new folder called HMS_auto, and this is the Cedar Creek folder, and these are all the files associated with the HEC-HMS model that we created in module 7. If you don't have access to that, this folder is provided to you with this module, so if you want, you can just go ahead and get that into your working folder, and I have named my working folder as HMS_auto. So once you confirm that you have an existing model, let's go ahead and open HEC-HMS. And we will browse to that folder where we have our model. So go to open, browse. So it is in folder called HMS_auto. So class HMS_auto, Cedar Creek, and cedarcreek.hms. And we want to make sure that we have already run the simulation. So if you go to results and look at your run one and go to sync one, and then we can look at the graph, and this is what we had at the end of module 7. This is the observed hydrograph and the blue is the simulated hydrograph. So in this unit we are going to perform auto calibration to bring these two hydrographs closer by changing some parameters. So make sure you are able to see this graph. You can also look at the summary table, and this will give you some information about how these two hydrographs compare. So the variables that you can use later is this Nash Setley, for example. So this is negative 1.6, and if the two hydrographs match perfectly, this value will be 1 or closer to 1. You can also see other statistics here, so root mean square error and then percent bias and so on. So it will also give you comparison of volume. So in the simulated hydrograph, the volume is 1.27. The observed hydrograph has a volume of 2.5, and this volume is given in terms of depth millimeters, and you can also see the peak of the simulated output 23.9 is much higher than the observed peak, which is 10.9 meter cube per second. If you are not able to see this information, or if for some reason your run 1 is grayed out, you can simply run the simulation one more time and you should get all this information. So once we have this simulated results, so what we are going to do is now, in order to perform auto calibration, you go to compute and click on optimization trial manager. You say new optimization trial. It will by default give a name optimization 1. If you want, you can change that. If not, you can just leave it, and then it will ask you all the files that you want to include in this optimization trial. So we have only one basin file, we will select that. Similarly, we have only one meteorological file, we will select that, and our optimization trial has been created called optimization 1. So in order to access this, you will go to compute tab here, and then earlier you had only simulation runs folder. Now you have optimization trials folder, and if you expand that folder, you will see optimization 1. So this is the information that we just provided, and what we are going to do now is we are also going to give it a start and end time similar to what we did for control specification file. So we can get this information from our control specification file. So if you want to access that, you will go to components, control specification, control 1, and you can see our simulation started on 21st February 2005 at 1 a.m. and it ended on 25th February 2005 at 6 a.m. and our time interval is 10 minutes. So I'll go to compute, back to my optimization one, and I will provide that information here. So 21 Feb 2005, start at 1 a.m. end at 25th Feb 2005 at 6 a.m. and our time interval is 10 minutes. Next, you will go to search tab here in optimization 1, and it will tell you the method that it is going to use to find the minimum of the objective function we specify. So simplex method is one of the methods. Another method that we have here is univariate method, and if you have taken classes in numerical methods, you will have some knowledge about this. If not, you can find information about this in literature or online. Maximum iteration is the number of iteration that we want the program to perform. If you want to increase the number of iteration, it is fine. It's just that it will take longer for the optimization trial to finish. So for now, for demonstration purposes, we will just leave this default as 100. But when you're trying to use this, you can play with that number. Tolerance is again when the optimization should stop. And here we are going to specify the objective. So our goal here is to bring those two hydrographs together, and if your error statistic or objective function that we are going to use is to bring those two hydrographs closer together, then our error should be close to 0. So we want to minimize, not maximize. So minimization is our goal. Location is sync1, this is our outlet, and this is the observed time series. So discharge gauge has our observed hydrograph, and then the statistic, there are multiple options here to select the objective function. So the most common that I use is the peak weighted root mean square error. So the idea here is that at least we should try to match the peak in case of simulating a single event where we want to estimate the peak accurately. So for now you will pick this, and later you can play around the statistics and see how your results change. So we pick that as our optimization function, and then again we can give our start date and end date that we have in the observed hydrograph data or control specification file. So 21 Feb 2005 01 AM, end date is 25th Feb 2005, and this is 6 AM. So once we specify this, our next goal is to include parameters that we want to optimize. So we will start with one parameter and see how the results will change. I'm going to add parameter by right clicking on optimization 1 and add parameter. And it will create an empty parameter, parameter 1, and then we will specify. So element, we will say all subbasins, and parameter is the SCS curve number. And it's a factor, so what we want to do is initial value of 1 means whatever value has been specified in the model, that is 1, and the factor is how much you want to deviate from that initial value. So we know that curve number cannot be greater than 100, so maximum of 100 is too much. So for example, if our initial value is 70, it will multiply it by 100 and you get 7,000. So we don't want that. So I will restrict this to 1.1. So it means that you can only go 10% more than what has been specified. And then also the minimum is 0.8. 8, let's say. And this range you can play around later depending on how satisfactory or unsatisfactory your results are. So let's go with this one parameter first and see how our optimization will perform and how close those two hydrographs come, and then we can add more parameters. So one thing to remember here is that you can specify the SCS curve number for all subbasins, but if you pick another parameter, that may not be available for all subbasins, and in that case you have to specify it for each element separately, and we will look at that later. So once we specify all the information that we need for optimization 1, and that information is the start date, end date, optimization method, number of iterations, tolerance, what kind of objective function you want to use, which gauge has the time series data, and again start date and end date in that time series data set. So once you specify all this, you can go to compute, and you can compute your optimization 1, or if your optimization 1 is selected here, you can also use this button that says compute all elements, and you'll click that. Now this says that simplex method must optimize at least two variables. So we specified only one variable, so let's go ahead and specify another variable. So to do that, you will click add parameter, and let's select a reach variable. So reach 1, and we use Muskingum method, so Muskingum k, and then initial value was 0.5, and let's say the minimum value is 0.5, which is what has been specified, and the maximum value, let's say 6. So we are adding this parameter because I got an error here that says simplex method must optimize at least two variables. I knew that, but I still just added one parameter at the beginning, just for you to know that you will get this error if you just run with one variable. So we added two variables, and when you specify a parameter, again initial value is what has been specified in the model. Minimum and maximum will provide the range within which the parameter will change. The other variable that we did not discuss with curve number is locked. So if locked is S, the program will not change that parameter. If the locked is set to no, then it is included in optimization. So we are adding parameters for optimization, so by default they are all not locked, so by default it is set to no. Now that we have at least two variables, the optimization should run. So let's go ahead and run that. And we have specified our number of iterations as 100. So if it reaches that minimum value within specified tolerance within less than 100 iteration, it will stop. If not, it will finish all 100 iteration. Since this stopped very early, so let's see how our optimization performed. To look at that, you will go to results, and then you will go into the optimization trials folder, optimization 1, and then there are tables here: optimization function summary, optimized parameters. So this is the table that will give you the optimized parameter value. So initially we started with 1, which is the default curve number the model has, and then the optimized value is 0.86. So what this means is all our initial curve number values are multiplied by 0.86 in the optimized parameter list, and our initial Muskingum K was 0.5, our optimized is 0.7. So let's go ahead and see how the hydrographs look. And again, there are other plots here. So objective function will show you how the objective function changed during the number of iterations, how the parameter value changed for each parameter we specified, and then finally we can look at the two hydrograph. So you can see our simulated peak reduced significantly, so it is much closer. And if we go and look at the sync 1 summary table, our initial Nash lift was minus 1.8 or 1.6. Now it is minus 0.9, so it has improved and there is still a lot of room for improvement. And if you want better results, all you have to do is you have to keep adding parameters. So what I'm going to do is I'm going to at least add all k values and see what does the program do. So add parameter, so Muskingum k, so this is 0. This is 0.5, so maximum is 6, so that is what we had provided earlier. So parameter 3, we will say reach to, parameter is Muskingum k, so minimum is again 0.5, and let's say this is 6, add parameter, so reach 2, now let's find reach 3, parameter is Muskingum k, 0.5, 6, add parameter, so reach 4, parameter k, 0.5 is the minimum, maximum is 6. So if you are asking me why I pick 6 as my maximum, this is something that will come to you by experience. So again, if you just provide a bigger range, it will take the program longer to find the optimized value. So we are at reach 4. Let's see, we have few more reaches, so reach 4, then we have reach 5, Muskingum k, 0.5 and 6, maximum value is 6, add parameter, so we have reach 6, Muskingum k, 0.5 and 6. So there are few more reaches. I'm not going to keep doing this. The goal here is to show you how to do it, and then you can do it for all the parameters for all reaches. So right now we have included k, you can also include x, you can also include the lag time for the SCS unit hydrograph parameter, and all that information is given in the handout. So let's run one more optimization to see how much improvement we'll get in Nash Sutcliffe. We may get an improvement, we may not. Let's see. So click on this. Since we added more parameters, this optimization trial may take little longer than the first one. So just be patient. And as you add more parameters, the program will just take longer to find the optimum parameter values. And once it is done, it will say 100% on both these bars, say close. We'll go to results. So look at the observed. So it didn't change much. But you can see the Nash Sutcliffe did improve. So even though visually we did not see much change, so from negative now we are at 0. Almost 4, 0.4. So our goal is to bring this to closer to 1 or hopefully greater than 0.7. Next, if you want, and you should, go ahead and add all Muskingum X, all Muskingum K, and then you can also add the lag time for all subbasins, and you can also play around with the objective function here and see what difference do you get. So let me go ahead and just do it and see what do we get. So peak error in discharge volume, so percent error in peaks. We already had peak weighted RMSE, so instead of something related to peak, let's pick something that is related to volume. So let's say percent error in discharge volume, and let's run the simulation. So I will save it, run the simulation. And hopefully you are seeing this graph is changing in the background as the optimization is going on. So you can see we picked a different objective function, and the objective was to match the volume. So the volume may be closer here, but you can see the hydrograph shape don't match at all. So maybe the objective function that we picked was not the right one. And this was just to show you what will happen when you pick a wrong objective function. So if I go back and to my earlier, which was to match the peak, and this is what I use most of the time, so I just wanted you to see what will happen if you pick a wrong objective function. So this is how you perform auto calibration in HEC-HMS, and after few iterations, when you are happy with your optimization, what you do is you find your optimized parameter values here, and then you input those in the components and in your basin model for each sub basin. So right now it is not changing your basin model, it is just giving you the optimized parameter value. But in order to actually incorporate those parameter values, you have to come back and make changes to your basin model with the new parameter set. So this is how you can perform auto calibration. So just continue these iterations until you are satisfied with your optimization. So this is it for this unit. So save your project, and even though the unit will end here, but you can continue and keep working on it until you get your satisfactory optimization results.